Okay, I'm going to talk about networking in the Ethos operating.
I was going to announce you, but I was also wanted to comment on the interesting war between having one CUBE's laptop and one Tails laptop at a conference. It's not the usual way at the presentation laptops fight with each other. So it's my pleasure to introduce John Solworth from UIC Chicago, who, as he already said to you, is going to talk about networking, in particular about Ethos.
Thank you for that very nice introduction. I would have also say that this is joint work with Dan Bernstein and Tanya Lang on some of the networking and other issues, and a whole bunch of students, and Janis Rux, who I've never met, but he's head of our German office for Ethos. So, okay. So the current state of the Snowden revelations, my take on it is to security and is much like Kenny's. To observers of security and privacy, none of the individual capabilities disclosed by Snowden was surprising. We knew that software was failing under attack. All software was failing under attack. But what was shocking was the breadth of activities and who it was aimed at. And Pogo had a great quote about this. We have met the enemy, and he is us. So Pogo was right. That's my takeaway from the Snowden revelations. And so now we have the war on us, and the question is, how do we defend ourselves? So I want to talk a little bit about software and why it is the way it is and what we're trying to do about it. So this is about software. When software meets the attacker, it fails almost always. We know one software, few pieces of software that don't fail, but for those pieces of software, you go at a lower layer and attack there, and it fails. So attackers have to work to make it fail. You see the breadth of activities that they've done in order to do that, but there's plenty of motivation. The U.S. budget, intelligence budget, is over $60 billion, and a significant amount of that goes for surveillance type things, whether it's satellite or whatever. So lots and lots of money. So what goes wrong? Well, there's a few things. Trust. We rely on those things that aren't reliable. Phil talked about the hierarchy used in X509. So you get a central authority that controls everything. Bad idea. If you're going to rely on somebody, you should choose. Weak security services, cryptography, authentication, etc., all don't work very well. And probably the worst of all is the fragile semantics that our systems are running, so that even if you get the security services right, you can go in and break the running programs that have the privileges and then do things with them. So, and the thing that drives all of this stuff is complexity, and it's complexity to program, to use, to administer, and to secure. And so our software base is this huge, sprawling mess of stuff that just is not thought out properly. Okay, so trust is the one issue that the users can't avoid. Everybody has different friends and adversaries, and you have to decide who they are and then decide who to rely on for some things. So you never need to you never want to rely on somebody else when you can do it yourself. But a lot of times, it's just, as you look at the world and you try to do things at large scale, you have to rely on people. That's the nature of society, nature of what things are. So what Tor nodes do you use? I know Tor picks them out for you automatically, but maybe they pick out the wrong ones. And you're sunk. What authentication services do you use? You have to get information that's reliable in order for the authentication to make any sense, assuming that you have strong authentication mechanisms. It's technically strong. You still have to rely on the people that produce it. What software should you use? What hardware should you use? So all of these things, kind of a dizzying amount of stuff that is much more uncertain given the way these systems have been corrupted. Of course, in computers, as the U.S. government has long been saying that if you go to China, they can take your computer and they'll add some component to it and they'll backdoor your hardware. How did the U.S. government know that? Well, of course they have the capability too. That's the best way to know that. And so, in a sense, it's good that they research it to find out those things. It's maybe not the best way that they've actually used it. Security services, password authentication is only appropriate on local machines. Yet we use it on the network, so that's just mind-blowing. And it's mind-blowing at conferences that we still have paper after paper after paper talking about password strength when no matter what you do, they're going to pretty much suck. So they really should be saying, what are we replacing passwords with? Authorization to limit what programs can do, isolation such as encryption, and the problems are, again, trust, key escrow. So I encrypt everything with a key, all my storage, I lose my key and I lose my storage, so I have to make copies of the key. But if I make copies of the keys, those are threats to me, somebody could get them and unlock my stuff. So how do I balance those out and build something that you don't lose your storage? Other kinds of things like authentication, that use is ephemeral and you can afford to kill the key, but when you actually have long-term data encrypted, you have to be much more careful. And so there's kind of trade-offs that have to be involved there. But, Phil talked about the difficulty of users doing various types of trade-offs, and I think that's true, but on the other hand, people always do trade-offs about their security. For example, when they lock their doors in their house, who they let into their house, what people they allow to stay in their house when they're not present, and all of these other kinds of issues, which are all security decisions, where they park their car, etc., which are all security decisions, and they make them. And I think that there's an appropriate level of computer decisions that are like that. So what's the problem with the semantics of our systems? A lot of the semantics is pretty fragile. We have problems with input verification in programming languages, buffer overflow, integer overflow, and buffer overflow in C maybe, but integer overflow in most languages. Operating systems, race conditions, isolation failures, aliasing like symbolic links. They enable attacks and they confuse the semantics, they confuse reasoning about things, because when you have these features in an operating system, you don't have to use those features for those features to be a danger to you. Services, inadequate isolation, authorization, authentication, encryption, all sorts of things, and network protocols, things like parsing and cross-site scription, injection, and CSRF. All of these things are designed into our software. In other words, they are not inherent. A lot of these things can be engineered out by thinking carefully about exactly what we want the things to do and avoiding all of the pitfalls that have not all of them, but avoiding a lot of the pitfalls that have caused problems in the past. One of the things that seems very common about security holes is any bug can become a security hole, but the bugs that seem to become security holes most prevalently are of certain types. They have to do with kind of a fractured underlying semantics of the system software. And so if we pay particular attention to those, we're not going to eliminate all bugs in all programs, but if we pay a particular attention to eliminating those bugs, then we can go a long way towards making our systems more secure. Complexity always favors the attacker. The attacker has to find one path that leads to compromise, from input to compromise of the system. And so they look for something that looks a little bit indigestible, bad news, something that looks like it might be a buffer overflow, for example. And then they trace back and see if they can excite it and trace forward and see what kind of damage they can do with it. And so it's involved, but but they have many, many more, right? The defender has one chance to make their system secure, and they have to check everywhere, and the attacker has many chances to find a hole in it. So, robust software is software able to withstand attack. Excuse me. So we know from the assurance literature that robust software to withstand sufficiently high level attack must be designed for secure above EAL4. Now EAL4 was kind of garden variety, top consumer level, top non-nation state level security, but it's clearly too low for what we're facing because the threat level is higher than that. Threat level is a government threat level aimed at your computing devices, everybody's computing devices. So aiming it for something that is kind of a hacker, something much lower than that, that doesn't make any sense. And so we need to design for security and have low complexity. None of our systems can be designed for security. You try to fix them, and you fix one thing, and other things break. You can't fix things partially like that. Once you start to make the changes that are large enough to get enough difference, you're just going to have to revamp everything. So we keep trying to fix them, and we get patches coming out every week, and security people know that it's important to do the patches, and non-security people know better, and they know it's important not to do the patches because the patches don't really solve anything, because there's going to be a new set of patches next week, and you don't know which are 0 day. So Albert Einstein said insanity is doing the same thing over and over again and expecting different results. It's time to stop patching things, and it's time to start designing things right. So in the Matrix, the lieutenant says about Trinity, I think we can handle one little girl. I sent 2 units, and they're bringing her down now. Agent Smith says, no, Lieutenant, your men are already dead. I think our software that we're using now is completely compromised. I think anybody who thinks they have a secure system either doesn't know or needs to talk to a mental care professional. So, I just don't believe it. Everything I see gets compromised, everything. So we started a project called Ethos. So the primary purpose of Ethos is to make it easy to build robust applications. Oh, that's really weird. It's an operating system. Why don't you make the operating system strong? So there's 2 different ways of doing research on secure operating systems. One is to make the operating system invulnerable to attack. Get microkernels and proving things correct, etc. But there's another way in trying to fix the semantics of operating systems so that the applications have a better base. We'll talk more about that. Ethos is a clean slate design. We started from scratch. Oh, we stole some code from someplace. But we started from scratch logically in terms of what the system call interface is. And it's incompatible, and that's great because it means it's incompatible with all of the mistakes of the past. Because what we do is we make mistakes and vulnerabilities and complexity in our software 30 years ago, and we keep using it and using it and using it and using it. Kenny talked about going back to 512-bit RSA because it was put in the 90s someplace to deal with export resist, and it's still there, and it still breaks. So, and we try to avoid things that haven't worked in the past. So Don Corleone in The Godfather, I hope some of you have seen The Godfather. I ask my students in my security course always if they've seen The Godfather, and there's a lot that haven't, but I don't understand how you could work in security without seeing The Godfather. So if you take away nothing else from this, go and see The Godfather. So it's an old habit. I spend my life trying not to be careless. Women and children can be careless, but not men. Well, that's very sexist. But in those days, the mafia was all men, so they were the ones, and they didn't touch the families. That was the code. And so they were the ones that are going to get killed if they were careless. And so how can we make the software so that we can feel that if our lives depended on it, we would be okay? That's the question we should ask. How could we make it invulnerable, as Dan would say? So I try to think about a lot of these things, and then when I don't know something, I ask Dan about it, and then he tells me what the answer is, and then I think about it some more. So, and it, everything, like time, thinking about time. You think time is simple, but time is not simple, because sometimes if you look at clock time, it goes backwards. And by 1 second maybe, but it goes backwards, and you have to make sure that your algorithms and everything is robust against that. It didn't use the wrong time value, etc. And so it's easy for the programmer to make assumptions which are incorrect, and it's made much more so by the fact that our systems are so complex and the things are needlessly complex in their semantics. So how does an OS affect security? Well, we already know what a TCB is. So a failure in the TCB might destroy your security. So we know that. But its impact is much larger than that. The semantics exported by the OS determines how applications can fail. And the easiest way to understand this is with a programming language. A type-safe programming language can't have buffer overflow, but of course C can have buffer overflow. So different languages give you the semantics that the language exports gives you different kinds of vulnerabilities. So the system layers have a profound impact on the security holes possible. And so we like to say that semantics is security. If we can design the system layers so that the rules are simpler, that the reasoning about things is simpler, then the people that build applications can build them in much more reliable ways, because bugs are, after all, a misunderstanding, a miscalculation. And if we can make everything simpler and prevent certain types of failures, combine those two together, we can make a significant step forward in making everything more secure. We go to extreme lengths to avoid security. People always telling us, this is too much. But they don't have secure systems. If they could show me a secure system and say, here, don't bother with all this stuff, you can do it with a lot less, fine. So, and the reason we go to these extremes is because even if we're this extreme, it's not clear that we can make the attacker's job hard enough that the attacker will give up. Right? So we have to make that attacker explore so many paths that they get more exhausted than the developer did. So we focus on one way of doing things. We've looked at software that has lots of different ways of authenticating, lots of different ways of doing this, lots of different ways of doing that. You go to configure something, just to pick up our mail. Check this. Do you allow passwords? Do you want crypto? Do you want this? Do you want that? This form, that form. Try to access your encrypted Wi-Fi or your set up a mail server. There's a whole bunch of questions that are all nonsense. It makes no sense at all that you're being answered all those questions. Why are there so many options there? So one way of doing things, get rid of all the crazy ways that don't make any sense. Unification. We take similar things and make them look the same. Unix did this by making files and networking and pipe all look like the same. File descriptor. High-level semantics because they fail more gracefully, so we don't want things failing at a very low level where the results are very unpredictable, but if we have higher level things, maybe they don't break as badly. Mindful of the pitfalls which cause security holes. So we have all these security holes out there. We want to abstract from them what the general rules are and then avoid those. Virtual machines for flexibility. We want to make things modular and small. And use declarations rather than code because that gives us decidability and we can run tools on things and better understand things and not try to worry about the code being generated wrong because the code is generated by tools. And ultimately, once we figure out what the semantics for the system is, we can then apply formal methods, et cetera, to harden up the system and make sure it's performing it right. And reduce the cognitive load on programmers just so that things are easier and you know more things and can reason about more things than now. So we use virtual machines. One reason is that it's hardware independent. About 2/3 of the code in a typical operating system is for device drivers. Maybe it's less than 10% in Ethos because the virtual machine presents one set of hardware. We can use other OS facilities like Cubes uses graphics on DOM0. You have a favorite OS application. That's fine. It's not your banking. Go ahead and run it on Linux, on Windows, on whatever you want to do. And you can simplify permissions and many other things by taking a look at this virtual machine and see how that can be married with permissions to make at least some things a little bit easier to do. Since you're already breaking things into compartments, then you can control how things run in those departments. So we want to make networking more efficient. So that only one network protocol, so these are unification examples. We want to maximize the commonality between Ethos native and Linux port of Minimalt, our network protocol. We use the file system namespace for networking rather than these port IDs. And we use naming to define permissions. Everything is tightly put together. You know, a lot of this is driven by learning from programming languages like in Go, when you make a variable that starts with a capital letter, it's exported and you don't have to export it or whatever, and you see the name and you know it's an exported variable. And so it saves you from looking it up or thinking about it. It's just burned into the language. So public keys are user IDs. So it's designed for the internet. Public keys are user IDs. Each user can have as many as they want. Pseudonyms. They're self-generated, and assuming the random number code generator is correct, they're guaranteed unique. Users are added on the fly. You come in with a network connection, and you've never been to that machine before. You get your own user ID, and then You don't have anything like in web servers where they have a list of separate users on the thing. You just need the keys in order to set up if you want to limit things, and you don't have to limit things. You can allow anybody to do it, but everybody is separated from one another. Domain names for naming, which are worldwide unique names that were the only source of worldwide unique names. And mobility connections, network connections, are not named by IP addresses and port. They're named by tunnel IDs, and that allows us to move them from place to place. So what's Ethos networking like? Well, we have data on the first packet, and all networking is encrypted for confidentiality and integrity. There's no way in Ethos to produce an unencrypted data packet. Ephemeral public keys are needed for perfect forward security. Tanya said, "Oh, we need perfect forward security." I said, "No, we don't need that." And Dan said, so we put it in. And public key authentication of users and servers, tunneling to inhibit traffic analysis, puzzles for denial of service, prevention of amplification attacks. So the prevention, mobility, so you can shut down your computer and open it up someplace else, get a new IP number, and continue your connections. Your connections don't break when you move. And preventing linkability across tunnels. So we use minimal stands for minimal latency tunneling. We use ECC, Diffie-Hellman, SALT, and we integrate this with authentication servers, and it's implemented on Linux and Ethos. So here's a TLS handshake. This is what you use with your browser. You first get a DNS. First you get a DNS packet. You find out where the host is. Then you do a SYN-SYNAC, which is kind of a weak authenticator. You use a randomized number generator, a randomized number to make sure that nobody can go and, interrupt your flow by sending bogus packets because they have to guess the sequence numbers. But we already have encryption in our protocol, so there's no real need for having that. And then there's a whole business with negotiating cipher suites, and Kenny showed that this is a fundamental problem, negotiating cipher suites, because you got all of these cipher suites, and you got a whole bunch of them that are breaking down at any given time. You have a whole bunch of parameters and all of this stuff, and they could be set wrong. And even if they're not set wrong, browsers and everything work in different ways, and they're possible to man in the middle. And so this whole idea of negotiating cipher suites in the middle of a protocol is a big source for error in the implementation of the protocol, and it causes extra packets. So that's TLS, and TLS allows a 2-round trip delay if you're reconnecting, and so you save some packets, but that's still 2 round trips. What does minimal do instead? Well, we have the permanent key of the server, so given that we can get the ephemeral key, the current key of the server, so we get our ephemeral keys from servers. They change over, they're good for a certain amount of time. You keep updating them at the server, and you get your new keys. And once you have the ephemeral key for the server, then you can request the ephemeral key for a host. That's the second step. It's a DNS lookup, but in addition to the usual DNS information of IP and port, we also have the ephemeral key, and it's authenticated so that we know we're getting information that we trust. And then here's the connection to the host. We connect from client to server, and on the first data packet, we have a request going. we have data running from the client. So data on the first packet, one round trip for directory service, as in any network protocol, and that's often a local server that's caching this information. And syntax is unnecessary. The cryptographic protocol eliminates the need of syntax. And if the tunnel's already established, the data goes, we create the connection, send the data in one packet too. On the packet, unencrypted, we have the IP and UDP for routing. The client ephemeral key for the tunnel initiation packet. The first packet it gets sent to create a tunnel ID, and a nonce for to decrypt. And the nonce is time-based, and that enables us to distribute our information about our time-based things. Tell you when the packet was generated and tells you what key to use for the server when it gets the packet. And it's integrity protected. Key rollover, keying occurs periodically, every minute or so. Key is a hash of the previous key, and is identified by a changing tunnel ID. When you change the tunnel ID, it looks like a new tunnel is being created, and we'll see why that's important for mobility. And so we provide perfect forward security over long-running conversations. You may have this thing up for days, and you still get perfect forward security every minute as we change that. For mobility, the tunnel is identified by the tunnel ID, not the IP and port. The tunnel, and so when we change the IP address, we simultaneously do a tunnel rekey, looks like a new tunnel, and inhibits the tracking of clients because you can't tell from a continued connection at a new IP address or a new tunnel being established, so you can't use that alone to determine whether that's the client you've previously seen in another IP. It's often said that it's really difficult to write secure programs, that secure programs are very complex and you have to reason about it. You have to reason about security, but to write secure programs should be just the way we write programs, and it shouldn't be inherently more complex. So here's our example. The client says, this is sort of our version of Connect. IPC gives a file system path in the IPC, and that authorizes it and everything. And it tells the computer it's going to example.com. And the server says advertise. That's kind of like a bind, but it's done on a name. And then we use that to import new connections. And when we import the connections, every user is authenticated, so we get a user ID with that. And we can use that to segregate different users and keep them out of each other's hair. If you use TLS, you write 1,000 lines of code, the TLS libraries suck, you go through all these stages, and specify all these things that maybe you don't know how to specify, and this is just embedded in the system. When you do a connection, it gets this. So the crypto's transparent, returns user ID, it's authorized by user ID. It's simpler than POSIX APIs for unencrypted communication, and application programmers can't screw up encryption or authentication. They can't fail to do it. It just happens automatically. There's no way of sending an unencrypted communication in Ethos. We have an authentication infrastructure that scales to the internet. The problem with authentication infrastructures is they've either been centrally controlled or they've been very inefficient. So the way to do authentication is you have a group of users, you get it from somebody you trust, and you use that to check the keys. And so you have to make that trust decision, but building it efficiently requires you to use names and everything, but we've got that built into the system. Denial of service protections, we mentioned some of them built into minimal. All information is typed. There's no requirement to serialize into some sort of protocol, and then you add in something else to the protocol, and you have to make all of these low-level changes, and it's hard to get right. It's a royal pain, and there's no parsing involved. We just take that and convert it. The system converts it to an in-memory structure. If the input is not in the right form, it will fail. So, and parsing just gives you a tree, and then you have to go over that tree, and maybe different people get different trees. So parsing is a lot more problematic. Control message done by RPC, start a new connection anonymously, start it with a pseudonym, close the tunnel, next tunnel ID, etc., things like that. Conclusion. Today's widely used systems have failed under attack. They're brittle, and when they break disastrously. They're unfixable and have to be replaced. We need systems which are much stronger, which means they're designed to prevent attack. Ethos is designed to drive down complexity and remove pitfalls while enabling strong security services. We focused on Ethos networking here, which is faster than unencrypted TCP/IP because it doesn't have the SYN-ACK. More secure than TLS because we have only one protocol and it has more properties, and it's very, very simple. Thank you.
Yeah, thank you very much for the presentation. Are there any questions?
Sure. Hi. Name? Ian. So great. One thing you pointed out correctly is that by removing all these options, you only give the user one way to do something, and it's a secure way, and that's great. But what happens when you discover, oh, we did something wrong, or there's a better way? Like, what happens when version 2 of Ethos comes out, and now you do have to decide whether the protocol is going to be version 1 or version 2?
Then you do the best you can. You do everything as the version 2, you make it the best you can without compromise. And if you need version 1, you run that in a different VM.
I mean on the network. Like when you're doing...
protocol?
Like protocol-wise, how do you prevent the rollback attack without having extra round trips?
So you're asking about versioning of the protocol.
Yeah.
So in the directory record, which contains the ephemeral key, I didn't mention it, it also contains the protocol number.
Okay.
So when you get that, you know what protocol that
So
server.
you put in the round trips that are hidden at boot time or whatever.
Yeah.
When you're doing the directory. Okay.
Hi. Thanks for the presentation. I've been following the Minimalt papers for quite some time, and I've been wondering where the implementation remains, because Google is moving really fast and pushing quick adoption. And so are you working on an implementation, and if so, in what?
So it's a lot of work to do. It's a lot of work to do an operating system. It's much more work to do clean slate. And in a university, we don't tend to push out very robust code if we make it available. So we've gone through a lot of the work towards release, but we're not quite there yet. So we went through all the code and made sure everything was implemented, not just the things we had to measure for the paper. And we went through and we cleaned up a lot of things. And we still have some things yet to do, so it's taking much longer than I expected. But
in what language did you implement Ethos for?
What?
In what language did you implement Minimalt for Linux?
Well, so so one of the things that we did, we had this Linux implementation going on, and it had like thousands of lines of code in it because we didn't have the Ethos system underneath it. And we ended up abstracting away, changing around a lot of things in our system so it could use identical code to what the Ethos kernel did. So that's great because those implementations are going to match up exactly, and I don't have to worry about, these things don't talk to each other. Why? Because or at least not very often. So we've been doing a lot of restructuring of things. So I'm sort of intellectually we're ready to release, but we still have a bunch more work to do. Since it's at the operating system level, we have sort of issues like we're tied to a certain version of Go because versions of Go after that made assumptions that are incompatible with our operating system and other kinds of issues that make this process just more difficult. So
And are you going to do any work to integrate it with like a web browser in terms of right now the Minimalt paper only mentions this approach for the initial session initialization with a central directory. Are you planning to integrate it with DNS or any?
So we have an authentication infrastructure, SAI, which is a distributed authentication infrastructure, which allows you to determine who you depend on to produce information. So the Sudsy work at MIT talked about forming groups for authentication, and so that's a natural thing to do. It's used all across computer security, and so that is being integrated now into the system. We're in the process of doing the code reviews and integrating it.
Thanks.
There was something that you had much earlier in the presentation that went by. I didn't quite catch it, and there was something you had up there about that the keys themselves were the user IDs.
The public keys, yeah.
Yeah, the public keys. That was a little confusing for me because in a lot of the systems that I've seen with public key crypto is you have a considerable amount of effort that goes to binding a public key with some kind of a name, like a PGP username, user ID, or maybe if it's a TLS certificate, it's tied to a domain name or something like that.
Yeah, I love the PGP names because they actually use domain names like that.
Yeah,
they use that natural name scheme.
And so in your slide, it kind of looked like you weren't tying them to names. Is that correct?
Yeah, because a particular key can have lots of names.
Yeah.
Right? So I can have a key stored under my UIC address, and I can have a key stored under some other address, and
okay, so you do
different
have
names for the same
key. You do have some kind of mapping between the names and keys. You got some kind of binding going on there.
Yeah, I mean, humans only talk about names in so there's sort of two issues going on.
I probably should have read the paper instead of asking you for clarification on that. Okay. All right, thanks.
Yeah.
I didn't quite catch the big picture, but so do you have any plans to make it? For me, right now, it looks like just an API provider for applications. Are there any plans to have it run on bare metal any time in the future? Or is it always going to be run under some other operating system or hypervisor?
Yeah, I would say that I'm much stronger on the usefulness of VMs than you are. Just the idea that you make the kernel much less monolithic by decreasing the number of drivers you have, et cetera, is pretty, and many other things, is just really attractive. And the other thing is that, the devices have gone so powerful that we have business on it and personal stuff and portable, that we have all these different environments that we want to keep separate. So we plan to use VMs forever. I would, if
you plan to be inside the VM forever. That's
right.
Okay.
That's right. If we're successful at the operating system
So you have no plans to have drivers under this paradigm, right? This is just for applications. Is that correct understanding?
What do you mean just for applications?
Not for drivers. I mean, you can't use it for writing more safe drivers, or can you? Can you use
No.
Okay.
I mean that's not the plan.
Okay.
So normally what you do is just spin that off into a different VM.
Okay, so my understanding is that Ethos is an API provider for writing more secure applications.
That's right.
Not an operating system. I just wanted to...
Well, not an operating system. So I would say an operating system is something that provides a process abstraction. So that's my definition of an operating system. So if you have some other definition, perhaps it's not an operating
Managing
system.
the hardware, right?
What?
Managing the hardware, the devices. Does the roll out the operating system?
Right, but what are the things that run in DOM-U? Are those operating systems or not operating systems?
API providers. For me, they are functional API providers. What's running in DOM-U? In CubeSub VMs.
Okay.
Okay. Except for the service VMs, which...
No, I'm not going to argue with your definition. It's a definition, right?
So the second question, you mentioned something like, because all the security problems are because of people making mistakes. I'm rephrasing it somehow. But what about intentionally malicious applications? How you gonna deal with these? Like backdoor intention.
Right. So in applications or in what, my application server? So one thing is that you have the system software layers that you're going to presumably do a lot of work to make sure that that they don't have backdoors in them. And then the applications, you're going to isolate them and do whatever else you do for them. That process should be simplified, but it doesn't cease to exist.
All right, I guess it's to me to end this discussion. I have a few housekeeping announcements. Please join me first in thanking John again for his talk.